today, the Hubble length today, or no, let's use this notation, right? Okay, so how do you dimensionalize this thing here? Well, you multiply, you divide by this, see? If it's 8 pi g c squared rho, and then we divide by this thing here, squared, then this thing will be dimensionless, okay? And this is the omega factor. This is the omega factor, okay? Now this thing, if we do all the numbers, then we would obtain something like, and we use the visible matter density. If we use dark matter density, then this would be of the order of 0.3, okay? And then 0.3 is a nice thing to work with, okay? So now notice that in this case, the making this dimensionless is multiplying it times constants only. We're multiplying this thing times a bunch of constants, so it's still a density. It's not another variable. It's a density that is multiplied by constants and in such a way to make it dimensionless, okay? And we can do the same thing, for example, this is for the density. Now, if we take the Hubble scalar and we divide it by h0, then this is also dimensionless, right? Well, we divide it by this quantity. It also becomes dimensionless, right? And so all what we're doing is dividing these quantities by something like this, right? Now, we also need, because for example, okay, let's call this thing mu. Mu by definition will be 8 pi g, let's say 3. Yes, yeah, we can.
We don't need to divide it by c.
Sorry?
We don't need to divide h by c. The new parameter that we have defined, h naught tilde.
Yes.
We don't need to define that. We just can use h naught.
Because there is some extra c square.
So c square.
Yes.
8 by d3 c4.
Ah, yes, if we use a 4 here. Yes, that's true. But, okay. Yes, okay. That's true. Okay. So, and here,
H naught is.
well, here is because we're assuming h to be 1 over centimeter. So here we do have to divide it by h. But anyway, this is, I'll show you how this is done. It's very simple. Okay? Now, we have this quantity. Right? This is now dimensionless. Okay. We're going to use it. And then we have this quantity, let's call it h, which would be h by h0 tilde. Okay. This is also dimensionless. Okay? Right? And then that's it. And then, for example, the fluctuations will be now d nu, which will be really 8 pi g over 3 c fourth h squared by this fluctuation, right? See? Fluctuation will also be, yeah? Because this is this, it's this. These are densities, and this is a constant there is, okay? So fluctuation is also made dimensionless. And the same with the fluctuation for h, okay? However, our equations of state will then be, for example, if we have the partial derivative with respect to ct, remember that t T, well, I write T, but really it's CT.
Yeah, it's a proper time, no?
Yeah, because, yeah, it's a proper time,
Of
and
observation.
we are using
That's
coordinates.
the coordinate, yeah.
Coordinates have units of distance, right? If there are angles, then they are multiplied times a distance. So the ds squared has units of square length, right? So really, we're using CT, right? Now, this, even though this thing, the mu is dimensionless, its derivative is no longer dimensionless, right? The derivative will have dimension of 1 over length. So to address this problem, we also have to make the time dimensionless. So what's the obvious choice to make the time dimensionless? Well, we defined another time, say tau, that will be simply h0 c cdt, which is ct, which is h0t. Right? That's it. We use another time. We use a dimensionless time also, right? And then the derivatives are also dimensionless, right? And then the whole system is dimensionless. And then we can, now there's another issue. This is the time axis, and so we are choosing to set up our dimension, the working of the dimensions at this surface. See, we're using h0. h0 is defined here, right? And so here we will get numbers that are of order of 1. But for very early times, we will get very large numbers, right? Which is okay. If we are interested in the evolution around in this era, this is our interest, then we don't care if very early times are very big, okay? But this is one possibility. Another possibility is that instead of considering t0 to be today's time, we can assume that t0 is, for example, the time of the last scattering surface. What is the last scattering surface? This is a cosmic time where matter, visible matter, baryons and photons, stop interacting. See? That's the time when neutral atoms form, because electrons are no longer interacting with photons, and so neutral atoms form, and the photons become free. There's what they are called free streaming. Photons then suddenly move very long paths, and they reach us. Now they're not exactly true, because there are a process of reionization, and the photons are not completely free. They still interact with the ionized gases and so on. But let's say the bulk of the photons are non-interacting and reach us, right? So this last scattering surface can be defined at roughly 400,000 years after the Big Bang, and it corresponds to a redshift factor of about 1,000, right? So why that surface is important? Because when this happens, when neutral atoms form, right? Then what happens with cosmic matter? There is dark matter, which is already decoupled. Dark matter does not interact with photons. Can be an asteroid of 1,000 kilograms of dark matter, and can come here, and it would simply pass him. Yeah. Now you would be hit because of gravity. But let's be a little bit more benign. Let's say not an asteroid of 1,000 kilograms, poor guy. Let's say a neutralino, a subatomic particle that comes and hits him. But it would pass through him like that. would not damage his cells or his DNA or his genes or his blood vessels, nothing, or mine. See, would simply pass us because there is no interaction. See, why this chalk, if I throw the chalk for, it's painful and the chalk breaks because the chalk is made of matter that interacts with his matter or with my matter, right? But if this chalk was made of dark matter, it would not interact, only gravitationally. That's why I use the subatomic particle, because the gravity from a single subatomic particle is negligible, right?
Dark matter may be made of heavy metal, heavy particles also.
Yeah, we don't know what it is. So as far it can be excrement of chicken. It looks like excrement of chicken, or it can look like subatomic particles or like asteroids. We don't know what it is. It can be scalar fields. We don't know what that's not the point. The point is that once visible matter decouples from the photon gas, right? So visible matter starts behaving like dust. And cold dark matter is already dust, right? So from last scattering to the present, we can safely assume as a very good approximation that everything that is not photons and neutrinos, which are negligible, their contribution is very small, it's dust. So LTV models are valid. LTV models are valid from last scattering to today. They're good descriptions of cold dark matter and baryonic matter, right? Before, they are not good. LTV models cannot be used in the radiation-dominated era because there is no radiation, there is no pressure, have no pressure. So an LTV model is not useful, is not valid before the last scattering surface. Whatever it does, the model before, is irrelevant because the model is no longer valid. It's not a valid description. Therefore, taking initial conditions at last scattering is also a good idea because that's where the models are valid, right? So this is the approach that I favor. Not taking initial conditions at today, but rather at last scattering. Now you can also take initial conditions today. So you take initial conditions here today, T0, and then how do you know what happened before? Well, you have to integrate backwards. Integrating backwards is also not a very good idea, right? Because in numerical processes, it's better to set your initial conditions at a given time and integrate forward, see how they develop. Not given some initial conditions to see what created them. It introduces numerical errors.
But
Right?
that you can manipulate mathematically.
Yes, you can do both.
Yeah.
You can do both, and
Yeah.
people do both. It's just a matter of convenience. It's practical and depends, etc. But both ways are possible. The point is, we have to make variables dimensionless, and we have to make time dimensionless as well, right? We have to make time dimensionless, okay? Both things I'm going to show you. Now, how do the equations would look like? Very, very simple. See? How the equations would look like. Let's see, the first equation. First equation is rho q dot, let me write it like this, equals minus 3 rho q times hq, right? Okay, so we define these variables, these things here, right? We define them like this. And we define this time, we define tau equals this, okay? So, and we substitute. So, we substitute this, we substitute, notice that mu q, that it's, if we multiply everything times 8 pi, let me call this thing well, let's write everything. 8 pi g 3 c4. This is d of CDT of all these. Well, but this thing is a constant, so we can write it also like this. Then this automatically is already d mu q by c dt, and then this will be equals to minus 3 mu q, because I'm multiplying this, and then here I would have hq, but hq is hq by h0 divided by c. Okay? Okay? Because remember that hq is, I'm just multiplying, right? Okay? Now, what we need, notice here, we simply pass this thing dividing. So this implies c over h0 c dt times mu k equals minus 3 mu q hq, right? And here the c cancels, but we know that this is our dimensionless time, so this is equal to d mu q by d tau. And then this is the dimensionless equation. It comes naturally, right? Okay? You see how we did it? And it works for the others. It's simply writing the equations in multiplied times the constants, and then working out the equations. See, here the dimensionless time came naturally, simply by dividing everything by this, right? See, divided by this, and here you have the dimensionless time. Okay? Okay? Now, it's interesting to see what are the units of this dimensionless time. What are the units? See? Let's do some, yeah.
It's not very clear. So, exactly what you are doing, you are taking proper time.
No, it's not proper time.
Yeah,
No.
it's not proper time, but you are taking CD.
It is a proper time.
Yeah.
It's a rescaled proper time.
Yeah. So
Let's call it something else. Let's call it psi. Okay. So that you don't get confused by this. Okay. Let's call it psi. Okay. It's a dimensionless time. That's all. See, the time coordinate for these models is proper time, right? So I'm just multiplying proper time times something that has units of the inverse of time. So it gets something that is dimensionless, but it's still proper time, it's just that it's rescaled. What we're going to see is, what is the scale? See, what is, when this thing has the value of 1, see, what does it mean? See, what time does it mean? This is h0, and then some t, right? What is the t when this thing becomes 1? A unit of it, right? A unit of it. How much is it? Well, it's going to be the Hubble time, right? Oh, see, we can compute this. This is the time. Let's call this the t is the time, so that satisfies this. So t asterisk will be 1 over h0, and this is 1 over 70 kilometers per second per megaparsec, right? So this is a huge number. It's it's seconds. Then megaparsec is about 3 times 10 to the 24 centimeters. And then here we have 70 times 10 to the 5 centimeters, right? So doing all these calculations, let's say 7, 10 times 4. Okay, so doing all this, it's about 3/7. 10, 24, I'm sorry, I have to use Spanish here. 10 to the 20. 10 to the 20 seconds. It's 10 to the 20 seconds. And 1 year is 10 to the 7. So it is like 10 to the 13 years, something like that. It's a lot of time. It's a very large time, right? So that means that evolution from, say, we say psi equals 0 is t equals 0. Suppose the Big Bang is in t equals 0. So when, and at that point, psi is 0. So 1 unit of psi is a huge time, right? And yeah, because this we have to see 10 to the 7 is 1 year, and then we have to multiply. I think it's correct. We have to multiply. It's about 10 to the 13 years. So it's a huge unit, right? So small amount of time, early time, it's like the last scattering surface in these units are going to be like 10 to the minus 6. They're going to be squashed very near the 0, okay? Okay? But present cosmic time will be, because present cosmic time is 10 to the, let's see, it's 1.3 times 10 to the 10 years. Yeah, it's a huge time. It's a lot of, it's an enormous time. So, but that's one possibility, you know. We can, if it's different, if we set it to be, and as this I will show you, if we set initial conditions at the last scattering surface, right? Last scattering surface took place 400,000 years, right? So the number of units of 4,000 years, or of 400,000 years up to present day is about 22,000, right? So if we set initial conditions at last scattering, then present cosmic time will be 22,000 units, right? And so 22,000 is still a manageable number. It's 4 orders of magnitude, right? And this allows us this gives us a very nice, very nice units to study all the evolution in between. So it depends on the problem. See, I'm not giving you a blueprint that you know exactly what to, depends on the problem. See, you can set up initial condition in your dimensionless time to be normalized by H0, and hope I didn't make an error. 70 kilómetros.
Just, I don't know, but
Megaparsec is 10 to the 24, this I'm sure. 10 to the 20, 10 to the 20 seconds.
Ten
Yeah,
to the
10 to
6.
the,
10 to the 6 in the denominator. 17 to 10 to the 5 is 17 to 10 to the 6.
where?
17 to 10 to the power 5 is 17 to 10 to the power 6 in the denominator.
Yes, here? Yeah, it's 70. Yes. But so if I divide here, yes, that's true. That's true.
10 to the power 18.
It's 18. But it's still like 5 orders of magnitude above our cosmic age.
10 to the power 11.
Yes, and yes, this is our cosmic age in years, and
10 to the power 11.
it's 11, right? It's 11.
The one that you have calculated, 10 to the power 13 years.
This?
This is 10 to the power 11.
Yes. Okay. 11 years. Ah, so. Yes, that's true. So it's about our cosmic age. It's about our cosmic age. Okay. So if we take, yeah, thanks for correcting me. Yeah, that's, you see, that's, people make simple mistakes. Yeah. So if we take this, the unit of dimensionless time here, it's about the same as our cosmic age. Okay? So that's in this case, then here's a Big Bang, and this is about 1 unit. This is E equals 1, which is not very good if you want to see what happened very early, right? Again, I emphasize that if we take the time of mass scattering is 400,000 years. Present cosmic time is about 30.7 giga-years, which is about 1.4 times 10 to the 11, 10 to the 10, right? Cosmic.
No, that is billion years. Billion is 10 to
Yes. Yes, it's million is 6, 9.
Billion is 9.
Yeah, no, but this is more than billion. No, this is correct, right? Years. So if we divide them, then there are about 20,000, things like 22,000 units, right? What I'm saying is that last scattering time is about 10 to the minus 4th. 10 to the minus 4 or cosmic age. Okay? So if we take these units, then all what happened in the early universe is very small, it's squashed like this, right? Okay? So that may be interesting if people want to see what happened from 1/2 of the age of the universe to today. So that's a good thing. But another possibility is to set up our unit here, and then here it would be like 22,000, right? Well, these numbers also depend on the model, okay? So we have to dimensionalize, okay? Now, once we do this, let's see how do we choose initial conditions. I would like to explain how we choose them, because there are several ways we can choose them, okay? So is this understood how we make the variables dimensionless? It's understood? Yes, just multiplying times the available constants and choosing the right time scales you want to study, okay? There are several options. So now let's see how our equations look like. See, we have our equations now, the ones we have to integrate, they look like this.
So please increase the font
What?
size. Font size.
Big. You have to write big.
Ah, okay. This is understood.
नहीं पर बहुत दूर में से इधर हटो फिर बहुत छोटा ही लिखने का आदत है बहुत छोटा ही लिखते हैं
The following one let's define mu q this way. Like this, with a 4 pi factor. And this H0, it has to be the Hubble factor at some cosmic age, right? The Hubble factor of the background, because that's another thing we're going to assume. We're going to assume that there is an FLRW background that is obtained if we take the radial coordinate and go all the way to infinity, right? The radial coordinate can also be made dimensionless, because the radial coordinate has units of centimeter. So H0 by C over R is dimensionless. If we need a radial coordinate, it can be made dimensionless in this way. Okay? Now, let's define it like this. And H is going to be, okay, going to be like this. And then the fluctuations will have naturally the same sign. If we do this, then our equations look like this. Also, we're going to define this, we're going to make the gravitational constant, we're going to make it dimensionless, right? And this will be 8 pi by G over 3 C squared. C fourth squared. Or let's do it. Let's keep it like this. Doesn't matter. So here it's mu plus lambda. Although there are good reasons to keep the 4. Let me keep the 4. This is lambda. Then the other ones, they look like D, U. And here, let me see, can you dictate to me? It's very simple. 3m minus dm minus 3 plus du. Then here's dh, right? Outside. Yeah? And then
minus 3.
3hq dm. Minus 3hq dmu. Then the other one, the h. How is it? How much? Minus?
1 by 6, Papa.
Sorry?
1 by 6.
Yeah, but 1 by 6, we have to incorporate this.
This is minus
This
3.
is, this would be minus,
3.
because k divided by 6 is 4 pi thirds. So it's really minus d mu. And then, what else? Minus,
dh times
minus what?
3. dh.
dh is at the end, but what's inside the parentheses?
3dh plus 2hq.
Plus,
2hq.
and then outside dh, right? Okay. So these are the dimensionless equations we need to solve. So what would be the initial conditions, right? One way is to choose initial conditions to say mu q at initial time t0, right? So mu q at initial 0 is simply 4 pi g 3 c fourth h0 squared, and then rho q0, right? This is an initial condition. We choose that, right? So we choose that, because and it's important that if we take the limit when r goes to infinity of mu q, it's, let's call this mu q0, right? Of mu q0, we obtain, this one should go to the background value, right? So what we are going to obtain is 4 pi g 3 c fourth h0 squared rho 0 background, right? And this is nothing else but 1/2 of the background omega, right? Okay, so this limit allows us to work out the numbers here, right? Because we already know, for example, if we take T0 to be today, so we say that this corresponds to dark matter, so this thing would be around 0.3. The background is going to be like 0.3, okay? So how do we choose mu q0? Mu q0 would have to be something like, let's call this would be mu q0, or let's say this would be mu 0 background. See? It would be something like mu 0 background plus a function that will be greater than that at the center, right? And will go to 0 at infinity. A good choice is as follows. Let's take this to be the central value minus the background by 1 plus r to the n. See? This is a good choice. Why? Because what happens when r goes to infinity? When r goes to infinity, this whole thing vanishes. And what happens at r, let's say mu central is mu q0 at the origin. Okay? So what happens when r equals 0? Then mu q0 becomes, see, if r goes to 0, then these two cancel and we have mu central mu. So this is one example of how can we construct this thing, right? And what would give us is it's a profile like this. It's a profile. This is mu 0 background, which is 1/2 of omega background matter, right? Which can be, for example, if we use a lambda CDM model, that could be something like 0.3 divided by 2, so it would be 0.15, right? And then we choose a central value. See? Let's say this is 0.15. So we choose a central value, let's say 0.4, right? And then if we choose this polynomial function, we will get something that will be doing like this. This would be our initial condition, right? For the density. See? This is if you want to describe an overdensity. How would you do if you want to describe an underdensity? Well, you just simply change the signs of these things, right? Well, in fact, you don't. The only thing you need is to choose a central value that is lower, that is less. And then you would get an underdensity if you do that, right? And this is how you choose your initial density profile, right? Okay? Now, we've seen how to do this for the density. Now, what we need the initial density, and then the initial Hubble time, once we have these two quantities, then how we calculate the initial value of the fluctuations? Do people remember how the fluctuations relate to the Q scalars? By derivation, right? Remember? Then we have d mu 0 would be simply like this. Okay? We've seen that formula. And the same thing for h. Right? Okay? Now, so far so good. We choose these variables. We integrate the system. We have the initial conditions. 4 equations, 4 variables, 4 initial conditions. Okay? Now, one question. It's very simple, very intuitive to prescribe a form of the density, right? We have an overdensity, that means lots of density in the center. The density dilutes. At infinity, we have the background density, right? Very simple, very intuitive. Okay? Yeah? Agree?
Yeah.
Now, can you please provide me an indication of what should be the initial Hubble expansion? Should it be something like this, or something like this, or like this? How would it be?
It should be like this.
Decreasing function.
Decreasing.
It can be, yeah, because we can reason that the background will expand faster, right? Or if there is an underdensity, the background will decrease slower, right? But it is still not very, it can be difficult to guess one way, right? In fact, it is rather difficult because this idea that if it's an underdensity, if it's an overdensity, it will expand slower, right? Because there is a density concentration there, right? But that can be tricky. That can be tricky. So it is preferable to use as initial value functions the quasi-local density, because the quasi-local density is like an average density, right? It's not the local density. Local density needs to be computed by adding this and this. Okay? So it is more intuitive to prescribe the quasi-local density and a dimensionless quasi-local curvature. Why? Because the curvature, the sign of the curvature is very intuitive to understand. What happens, suppose cosmological constant is 0. So what happens if the spatial curvature is positive? What will the models do? No. It's not a closed model. The topology is not closed.
No, okay.
The evolution.
Evolution.
If cosmological constant is 0 and spatial curvature is positive, then the configuration will expand, bounce, and collapse.
That's
right?
Yeah, close. Yeah.
Right? On the other hand, if curvature is negative or 0, will expand forever. So it's very intuitive, right? If it has a lot of curvature, it will expand faster. If it's positive and it's a lot of curvature, it will collapse faster, right? And if the curvature is positive but very small, it will collapse but take a long time to collapse. On the other hand, if spatial curvature is negative, it will expand. If it is very negative, it will expand very fast. So spatial curvature is more intuitive, right? It's more intuitive to see what will happen, okay? So.
But spatial curvature is also dependent on how much matter you have, no?
Yeah, but no, Special curvature, see what happens is that because of the Friedman equation, Hubble, special curvature, and density are linked.
Linked, yeah.
Yeah, so, but no, it's an independent thing. It will be related to the Hubble. Given a velocity, it's not a direct, it's a relation between three things,
Three things.
right? It's a relation between three things. You can modify two of them and obtain the other, right? So, these two, and even if there is cosmological constant, because remember when we saw the energy diagram, if there is cosmological constant, then it's possible to have models with positive curvature that expand forever. But the curvature cannot be very large. If the curvature is very large, even these models would collapse. Nevertheless, the curvature is more intuitive, right? So we have not defined, we can define kappa q, which would be simply the kq divided by h0 squared multiplied times c, okay, times c squared. So this is the dimensionless. Curvature, right? And we can use it. And then once we have it, see, the procedure is now as follows. We define as initial conditions mu q0 and kappa q0, right? Now, how do we choose kappa? Well, for example, if we're working with a lambda CDM model, then the lambda CDM model has zero special curvature, right? So our kappa should go to zero in the background. If we go to infinity, we reach the background, which has to be lambda CDM, so that curvature has to go to zero as r goes to infinity, right? If we have another background, then we choose it. It depends on the background. The background essentially gives you this constant here. Gives you this constant, right? The constant that it will tend, right? And then you modify depending how much you want it to be bigger or smaller in the center, right? Because in spherical symmetry, you only describe one inhomogeneity, right? Okay? So, once we have this, what is the next step? The next step is to compute once we have this, we compute HQ squared, or let's say HQ, which will be equal to the square root of 2 MQ0 minus kappa Q0. See? So once we get these two, immediately we compute the third one, right? Okay? And then we compute d mu 0 by and that's it. We're ready to integrate the system, right? Okay? And this is what I'm going to show you now, how it is done now, that's one point before going into that is the following. See, these are our definitions, so I'm not going to erase them. We have to integrate these differential equations given these initial conditions. But these initial conditions depend on R. Okay? So, how do we implement these initial conditions? They depend on R. So how do we implement them? Well, the way to implement them is, here we have our time axis, and here we have the axis, the R axis, right? So we make a partition, see, because this is numerical, see, we go from a minimal value of R, which will be 0, to a maximum value of R, right? Which is arbitrary. we can choose it, because remember that the arc coordinate can also be normalized. See, here the arc coordinate can be also normalized. See, depends on the scale. We can choose the scale. Depends whether we want to study one galaxy or a group of galaxies. See, that gives us the choice of the maximal radius. And then we make a partition. Right? Right? This is 1, let's say. This is a fixed value of this partition, right? So we solve these differential equations as if they were ordinary differential equations with initial conditions given at each point of the partition, right? Because if we fix R, then the initial conditions are constant, but only for this R. But since we do it for the whole partition, then if the partition is sufficiently thick, let's say the partition has 200 elements. So what we have to do is to integrate this system 200 times. But it sounds horrible, but Maple does it in a few seconds. Maple does it faster than the time I have to stop and light my pipe, or to stop and I don't know, go for a walk, go to a toilet. To a toilet, it's already done. Okay, but this is the way to do it, because this, even though they are only time derivatives, these are still partial differential equations. The effect of the radial coordinate is in the initial conditions, right?
How you can say, how you can fix this number 200 is just like...
No, just a guess.
Yes, yeah.
50
Yeah.
or normally 100 are sufficient. Even 50, partition of 50.
Means to get solution of this equation.
Yes.
Okay.
Yes. Now, the simplest way is to put the partition in equal radius. But there is what is called the adaptive mesh. What we're doing is a one-dimensional mesh, because it's a one-dimensional problem. Initial conditions are given along the radial variable. If we had, for example, with Sekhere's models, that's not true, because your space of initial conditions is three-dimensional. So with Sekhere's models, instead of 1,000, it would be like 1 million. Well, yes.
1,000 raised to 3.
Yeah, 10 to the 1 million.
Billion.
Yeah, but it's the radial partition is larger than the angular. Like the angular partition is like 10. For Sekhere's models, it would be 100 times 10 times 10, 10,000 times. Right? Here it is only 100. Anyway,
Here we have only one type of initial condition, no linear.
it's a one-dimensional
Yeah,
set.
one-dimensional.
Initial conditions are a one-dimensional set. That's the difference. So let me show you how it looks like. Let me show you what it does. Okay, so first, this is a program to write up initial conditions. These are the equations that I've shown you. There are equations that we've written, and includes also the equations to find the metric functions, right? Okay. And then, there's all this explanation. I set up my initial conditions at last scattering surface. So I have to compute the omega factor at last scattering in comparison with the omega factor today. And so here are all the numbers, and I do these calculations, and then the omega factor is going to be at last scattering is negligible. It's 10 to the minus 9. But this even though it might look to you negligible, it makes a very strong impact in the late time evolution, right? Okay, the first procedure is you prescribe this thing, right? This is exactly what I've been showing you in the blackboard. Now, here I'm doing it another way. People didn't ask, so I'll say. People tell me, well, you are prescribing the initial quasi-local density, but what can you prescribe not the quasi-local initial density, but the standard initial density? Yes, you can, because remember that if you know rho 0, how do you find rho q0? Well, you find it by an integral. Right? You find it by an integral. If you know this one, you find rho q0 by integrating. Okay? It's more difficult, but it's possible, and especially if you do the integral numerically, then it's straightforward. And here, in this case, I was working with my colleague in South Africa. He said, no, that quasi-local density, that I don't understand what's that. Use a normal density. Okay, so no problem, we use the normal density. Here, I'm prescribing, notice absence of the index, subindex q. This is standard density, right? Standard density, defined in this way, standard curvature, and then we find the quasi-local ones by integration, right? Remember that R at the initial slice, big R, is small r, right? So this is how we find all these things, right? And so this is a procedure. It's a Maple program. I won't go into details, but I'm just telling you what it does. What this program does is that, what this program does is that you give a polynomial form like the one I wrote. Very simple. Maple tells you that M is, it allows you to define your M as any way you want, and then it calculates all the initial conditions. It calculates all the initial conditions that you need, right? And of course, there is a glitch, a possible glitch, if this is a square root here. So if this square root is negative, then it's an imaginary number, and so the procedure has an error saying that it calculates this integral, and if this integral is, if the integrand is negative, then it warns you, it stops, says error, incorrect initial conditions. So then it calculates everything, and then I define global variables, because what I'm going to do is that in Maple, you define, once you make a program, there are two types of variables. The local variables, which are valid only inside of the program, and global variables, which are constructed by the program and can be used outside of the program by Maple. These are global variables. So the final initial conditions, I define them as global variables because I will work on them, right? I will do another program that will work on them, okay? So this is saved, this is stored in a safe command, and it is stored in this binary file, okay? Now, once I've done this, I have another program. There's a numerical integration. This is a summary of everything, right? Glossary of terms. Can people read?
Yeah.
Yeah?
Yes.
Okay. So this is just an explanation of everything that I've been telling you in the blackboard. It's explained here with all detail, central values, background values. This I use for the entropy growth. See, the entropy growth for LTV models can be obtained from this formula. It's complicated to explain how, but let's say, suppose this is what I want to compute, right? But to compute this, I need these fluctuations, HQ. So I have to run the program to compute these things. And then what I do when it's computed, we plot it, and we see it. The output of all these are graphics, right? There are graphics that when you do something numerical, your solution will be a graphic. Well, your solution can also be a table, but tables are not so illustrative as graphics, like the old proverb says, one picture is worth 10,000 words. So one graph is worth 10,000 tables or 10,000 pages of blah, 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 blah. Okay? So these are the quantities we have to compute. Then there is another thing that can be computed here, and it's called the growth suppression factor. The growth suppression factor is one quantity that can be observed. It can be people who look at motions of galactic clusters, because the idea is that structure formation is not a process that is, it's a process that cannot go on exponentially. It has to be suppressed, because if it's not suppressed, we would see a lot more structure, but we don't see so many. So it means that growth of structures is being suppressed, and this can be computed. And if we take the computation that people do for FLRW models with perturbations, and we translate this into parameters of LTV models, this means that we would have to compute these things, right? So these things are of interest, and so we want to compute them, right? Okay, so this is like a prologue. Now, usage of the initial conditions routine. We load the file, the binary file here, and this is the syntaxis. This is the syntaxis that we're going to do. See? Let me see if... this is the way we're going to use the procedure. See? This is the instruction. When you program, you generate a new instruction. And then here, put see, let me write it like this. This. These are the things that I'm specifying in the routine. I'm giving an expression for the initial density, for the initial curvature, and giving an expression for omega, and also giving an expression for the background value of H. And this is the parametrization of R at the initial slice, which we will take to be simply f of R to be R. This is the range of the partition, see, from R1 to R2. Normally R1 will be 0, and this N is the number of elements of the partition. See, the thickness of the mesh, right? Okay? So these are the evolution equations that have to be solved, the metric, 6 equations for 6 variables. These are the equations we have to solve. This is the dimensionless time. It is calculated a bit differently here than what I showed you. Big Bang time is not simultaneous, but non-simultaneity is negligible. We will compute that. Okay, these are, now, first example. First example, we assume a lambda CDM background. This is important because this will help us. In fact, what's the difference when lambda CDM, well, that cosmological constant is non-zero, right? And also, spatial curvature has to be chosen so that it goes to 0 at infinity, right? If you choose this background. So we run the initial conditions, And here, this is the points of the partition. See, the radial values of the partition. Okay. And this is the value of lambda. And then we start plotting things. These are the plots of the initial conditions. This is the plot of the, it's not the quasi-local, but it is the local and quasi-local density, right? The local density is the thick curve, and the quasi-local density is the dotted curve, right? Which both of them I can obtain from the initial conditions. See, special curvature. This is a special curvature. Again, the local one is a thick curve. Notice how it tends to 0 at R infinity, because that's the lambda CDM model requires us. Okay? And then, okay, now we are going to solve the equations. I think it's better if okay. We're going to solve the equations. This is a routine to solve the differential equations, right? It is dissolved, and then I write all the equations here. These are the equations that have to be solved, the 6 equations. And then here, here you can see, here, these are the differential equations that have to be solved. And here are the initial conditions. H evaluated at 0, H0, 0. I have defined the dimensionless time so that it is 0 at the initial slice. Therefore, the Big Bang will be at negative values. Okay? This is also convenient, but it depends on the, see, there's no blueprint for this. It depends on, and to do this you require skill. Okay? Now, these are the initial conditions. Okay? And here is the end. This is telling Maple how, because the initial conditions will depend on one parameter, namely the radial coordinate. So this is telling Maple that the initial conditions will depend on 4 parameters. And this is also something you need to, this is part of the way you solve these differential equations in Maple, right? Okay, so here this is done. And then once you do that, once you solve that, it is important to tell Maple that, see, it's very important in numerical solution to be able to assign a name to it, right? So suppose I get the density, and it's numerical, but to invoke it, to be able to invoke it, it's useful to give it a name, right? To treat it as a normal function. It's a normal function that cannot be treated analytically, but can be evaluated numerically. So what I'm telling here to Maple is going to find MM numerically. And I'm telling Maple, please give the name M to MM, so I can use small m to evaluate it. So you'll see that. And then here is the, we do the same for all of them. And then what I need to, the last thing to do is to be able to identify the initial conditions with a list of numbers. Okay? And well, here these are all, whenever you do this, you have to check that everything is consistent. And this is some consistency checks that I do. This is the way you are going to, this, for example, this computes H for the word line 40 at the time, at the initial time T00. T00 is present cosmic time, right? So Wow. Then checking absence of shell crossings. This is, to test absence of shell crossings, you have to test that the function gamma is not zero. So I evaluate this function for the world line 30, the world line 20, the world line 10, at very, very large times. And see, since they're not zero, this means that it's very unlikely that there will be shell crossings. And then the non-simultaneity of the Big Bang, what I do is that I evaluate the density at extremely early times. And then Maple tells me, your singularity is minus 0.66. This is for the world line number 2. And for the this is like for the world line near the center. And for the world line near the other extreme, the singularity is at 0.666. This means that the difference of cosmic age between the center and the extreme is of the order of 3,000 years, which is nothing. See, our cosmic age is 13.7
6 billion.
billions years, so 3,000 years is nothing. So although the Big Bang time is not simultaneous, the difference between ages is so small that it's practically simultaneous. And then, here are the plots. This is the graph of lambda, of omega. See, how do I compute omega? Well, I tell Maple to plot this quantity. This quantity here, this quantity is omega, because omega will be the density divided by h squared. Remember, the density already has incorporated the 4 pi, and this is what we get. See, this is present cosmic. No, let's see. Yeah, this is the time axis. This is the time axis, and then the age is normalized by 1. So exact this value 1, this is present cosmic time. This is present cosmic time here, right? Present cosmic time. This is an underdensity. So at the initial conditions, omega was very close to 1. Then in the background, or this very close to the background, omega is decreasing, and at present cosmic time it reaches the value 0.27, which is consistent with observations. However, this happens at the background. Near the center, the omega goes much lower, much lower, much lower, and it takes a value that is very close to 0, as it happens in a void, in a density void. So this is the first plot that shows that everything is okay. Now what happens with omega lambda? With omega lambda, what happens is that at the center, omega lambda is basically, let me orient this thing here. Yeah. Time axis is here. Let's see. Oh. Lambda. Yes. Yeah, this is at the beginning of the the beginning of the evolution, omega lambda is almost 0, negligible. But it grows, 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 grows. And then notice here, at the center, omega lambda has this value. But near the background, omega lambda reaches a value that is about 70.7, which is again also consistent with observations, and is consistent with the lambda CDM model. But notice how this parameter, in an FLRW model, this parameter would have simply this evolution. With perturbations, you would have a very small variation. But since here it is not perturbation, it is, you see the non-linearity effect is that there is a very large variation. There's like a 20–30% variation, right? This quantity. Then this is the omega of the curvature. The omega of the curvature, it's near the horizon, it's almost zero, but it varies a lot in the center. So this is the effect of the inhomogeneity. See, this is what happens near the FLRW background, and this is what happens near the center. Then the fluctuations. These are the relative fluctuations. This is the density fluctuation. See, the density fluctuation, it's almost zero near the background, and then it has grown a lot at present cosmic time. This fluctuation has grown from almost zero to more than 1, which is a non-linear value. This is the fluctuation of the Hubble scalar. Fluctuation of the Hubble scalar is almost zero at the beginning, and then it becomes negative. I think this is negative. Becomes negative, and this is the fluctuation of the Hubble scalar. And then this is the this is like the growth suppression factor. This is, again, all these things are the things that I wanted to calculate are here. This is the growth suppression factor, and here this thing is the value today, right? Because we're studying this growth suppression factor, how it evolves from initial conditions to present cosmic time and further into twice our cosmic age. The growth suppression factor, again, this is another calculation. Okay? And then we can make two-dimensional plots. Like this is delta. Delta is the dimensionless fluctuation of density divided by the scale factor. We get this graph for a typical observer. It will change from one observer to the next. And this is the suppression factor, and this is the entropy variation. See? The entropy, this is the density, the derivative of the entropy. Notice that it's positive, all the time is positive, but it comes a point where it starts decreasing. This is a derivative that is positive. That means that the entropy is increasing. But it is increasing, and then the growth of the entropy will be suppressed. And this is another plot, right? Two-dimensional plot. Now, here we do the same thing, but with another background. This is the Einstein de Sitter background. It is zero cosmological constant and zero spatial curvature. So the behavior of these quantities is very different. But we do the same calculations, and where is the difference between one background and the other in the initial conditions? Right? And we get very different behavior, which I'm going to go quickly through it. We do the same thing. We integrate the equations, we give numbers to them, we check absence of shell crossings, non-simultaneity of the Big Bang. Now look at the omega of dark matter. The omega of dark matter is extremely high. In the background, it starts with 1, and then present cosmic time has decreased to like 0.85. And this is the behavior of this quantity near the center. And then this is the curvature. The omega of curvature is almost zero, has to be almost zero here, but then it decreases. And again, all these quantities are computed. All these quantities, the same quantities are computed. The same quantities. Okay? I'm going to go quickly through this. Same quantities are computed. Then this is another example. this is a free, the background is now FLRW, but with negative curvature. This is called the open FLRW model, right? And so we do the same calculations as before. Here we have to change the initial value functions because curvature now is not asymptotically zero. See, you see, this is a special curvature initially, and it does not tend to zero, but tends to a small negative value. Okay. Then we do the solutions, the same, blah, blah, blah. You've seen all these. Here, look at omega. Here, omega starts very high, but at present cosmic time has reached 0.3 instead of 0.85, right? So it has reached 0.27. And yeah, we do the same thing, same. All these graphs, same graphs, etc. And finally here, here's an open FLRW background with another parameter, so on. We also take this, and same thing, and finally we reach the conclusion here. Open 2, yeah. We put the plots, the joint plots together. And here we can see how the suppression factor behaves for a typical observer. Here, this is the case for an Einstein de Sitter model. Is the Einstein de Sitter, zero cosmological constant, zero curvature. In this case, this suppression factor does not do any suppression at all because it grows. So this is one of the reasons why these models are discarded, because if these models were true, there would not be any growth suppression. Structures would be forming and forming. Now, the black case is the lambda CDM model. The lambda CDM model, there is a suppression. The suppression factor goes over, decreases, and this is here. This is the FLRW open model. This shows that negative curvature also has an effect of suppressing structure formation. But what happens is that for early times, negative curvature is a stronger suppressing factor. But this thing here will move like this, and this thing will move like that. So that very large cosmic times, the cosmological constant is more suppressive than negative curvature. So we can see it from here. Then comments, blah blah blah, and then this is the another plot, a very similar plot, but taking longer cosmic time. See, again we see that the cosmological constant is the suppression factor. See, this is present cosmic time is here. So present cosmic time, we cannot distinguish them. At previous times, this one suppressed structure formation much more than the cosmological constant. The cosmological constant is negligible for early times, right? But if we go for longer cosmic times, then cosmological constant is a stronger suppressing factor. But at present cosmic time, we cannot tell very much the difference. That was the point of this argument. In fact, it's an argument I have with a colleague who claims that he made an error because he thinks that these models behave like this, and it is wrong. This model, in fact, this is an ongoing argument, and it's I think we're going to publish it soon. And then comments. Then this is the behavior of entropy production, gravitational entropy production. You can see how suppression factor is strongly tied to entropy production. See, this is the entropy gravitational entropy. Gravitational entropy, which I hope to be able to explain tomorrow what I mean by that. But gravitational entropy grows a lot for these models because these models do not suppress growth. Essentially, gravitational entropy is related to how much structure is formed by gravitational clustering. If a lot of structure is formed, this means that there is a lot of gravitational entropy, right? Equilibrium is equilibrium is homogeneity. In FLRW models are in gravitational equilibrium. They don't form structure because they are homogeneous. If you put a lot of inhomogeneity, then a lot of structure. But it's not only density, also velocities are involved and curvature. Now these models have zero curvature and they're very dense. Therefore they form a lot of structures, right? Now, this is what happens with a cosmological constant. Cosmological constant, entropy growth is increasing, but then starts to decrease. And these ones, gravitational entropy basically grows logarithmically. So this curve, in the end, will diverge, and this one as well, but it will diverge logarithmically, while this diverges exponentially. And this one, cosmological constant, is the only background in which gravitational entropy production tends to zero asymptotically. And this is a nice result that I published like 1 year ago, that of all these models, gravitational entropy tends to a finite value, because remember, this is dot SGR, not SGR itself. If you integrate these curves, what you can see is that this one tends to infinity logarithmically, this one tends to infinity exponentially, and this one tends to a finite value. And so only if you put gravitational cosmological constant, this gravitational entropy will tend to a saturation value. And this is found by these plots were put in this in that paper of gravitational entropy. And here's some comments, and then the joint three-dimensional plots are here. However, notice that this what we did was to take an average, was to take a representative DOS layer. But here you have all the DOS layers in the partition. We used a partition of 50, right? And then